These are your notes. This lesson is not in your textbook. It's from the Algebra 2 book. So I copied the lesson from the Algebra 2 book so that you'll have some different examples to look at and not just your notes to look at on your homework in case you want something else to look at since it's not in your textbook. Yes. Because it's not in your textbook. So a step function basically is called a step function because it looks like steps when you graph it. And we have a special type of step function we're going to look at. But before we do that, I want to give you sort of like a real example of this. So you can kind of shorten this up a little bit if you want. But here is here's a shortened version or a real life example of what a step function would be. A therapist charges $20 an hour. Anything over an hour will be charged at 2 hours. So 1 hour and 5 minutes, you still get charged 2 hours. What would a graph of this look like? It's going to look like a step function. Well, I think usually you only go, like, places like that charge by the hour, it's like 45 minutes, so you have like a 15-minute leeway. But still, 45 minutes, you're still going to get charged an hour. If they just round up. What else is like that? There are lawyers like that. Do they round up to the nearest hour? So I know they charge by the hour. Well, they're like $400 an hour or something crazy like that to be a lawyer. No. You're surprised by that, aren't you?
You like your therapist? Can you go out and like yours? Oh, my physical therapist? No, not really. I like my physical therapist. My occupational is kind of sketchy.
So let's make our x-axis hours. So I'm going to go 1, 2, 3, 4, 5. And if we're talking about how much we're getting charged, if our x-axis is hours, what makes sense for our y-axis? Money, how much we're getting charged. And since we're going in increments of 20, I'm going to make my y-axis go by 20s. So anything from 0, we'll say, not really that you're going to be in the therapist's office for 0 minutes, but anything from 0 all the way up to 1 hour, how much are you going to get charged for that? $20. So to show that, we could say from 0, technically if you were there 0 minutes, you wouldn't get charged anything, so I'm going to make an open circle there. And then all the way up to 1 hour, including 1, that whole little increment from 0 to 1 hour, I would be charged $20. But what happens at 1 hour and 1 minute? It goes up here to 40, and it stays at 40 all the way to 2 hours. Do you agree with that? And so could I say from 1 to 2 is going to be $40. And the way I'm going to show that is I'm going to put an open circle on 1, because 1's not included, and a closed circle here. You see how that kind of looks like steps when you do it? What do you think open circle means on a graph? Not included, closed circle means it is included. This shows that it's still a function because it still passes the vertical line test, because this is not included and this is. But technically, I can't just say at 1 hour and 1 minute. Like even at 1 hour and 1 second, technically that would round up to 2 hours. They wanted to be a stickler like that. So we have to start all the way at 1, but not including 1. And then everything between 2 and 3 hours is going to get charged up here at $60. 2 is not included because at 2 hours it's only $40, but 3 is included, and then you get that little stair step.
So what's the like on?
Because this is at 0. Technically, at 0 minutes, would you get charged $20? But what about at 1 minute? Would you get charged $20? And so that's what the open circle means. It's just not included. When you make a step function, one side will always be open and one side will be closed. Which side will it be? Well, it kind of depends on the problem. If it's a story problem, about rounding up, it will always be like this. But does that kind of make sense of what a step function looks like? Justin.
Yeah, I can tell the second one, the third one. Circle all that.
This one's not filled in either. Notice this was an open circle.
Yeah.
This one's not filled in because at 1 hour, what would you be charged? So that's why down here is filled in, and I have the same open circle up here at 20. Open circle means it's not included because at 1 hour, it's not really $40, it's $20. Does that make sense? It's just kind of a way to show that it's not included, but everything from 1 to 2, kind of like if we were writing this in interval notation, we would write parenthesis 1, but bracket 2, because the 2 is included and the 1's not. And to show that on a graph, we just do an open circle versus closed circle. Okay? And so that's a story problem with the step function. No, it's a step. There's definitely a discontinuity in between there, yes. Because nothing happens in between here. Like, it jumps from 20 to 40. Like, you would never get charged $30 at this therapist's office. It jumps, which is why it's called a step function. What we're going to talk about is a special type of step function in algebra called the greatest integer function. The greatest integer function. And the idea of the greatest integer function is very similar to my little therapist problem. It has a weird little notation here. The way they denote the greatest integer function is they put brackets and then like little bars that kind of look like absolute value bars, but they're not. And that means greatest integer. The Algebra 2 book always shows it like this, or sometimes they even show it just with 2 brackets, not the straight lines. The pre-calculus and the calculus book just write this. They write int for greatest integer, and then they just put parentheses and then the function in there, x. So it's definitely a new kind of function that we haven't seen before. And it has its own little definition here. The definition of the greatest integer function means no matter what you plug into that function, you will always take the greatest integer less than or equal to x. And so I put my own little definition in there because the greatest integer that's less than x, sometimes greatest and less in the same sentence, is a little confusing. But basically, no matter what you plug into that problem, you will always round down to the next lowest integer. That means, kind of like our therapist problem, you will never get a decimal or a fraction out of this function. You will always get an integer, because no matter what you plug in, you round down to the next lowest integer. The hard part is we're so used to normal rounding rules that we tend to struggle with this, because we want to round the way we've always round, where 5, you round up, below 5, you round down. So we're going to practice first. I hate that this moves all that. So if I said evaluate the greatest integer of 7.3, you're going to round down to the next integer. What would be the next integer rounded down from 7.3? 7. What about 7.9? What would you get? 7. You round down every time. So even at 7.9, that's going to give you 7, not 8 out of that. I kind of wrote these a few different ways to make it think here a little bit. This one means the greatest integer of negative 1.5. Negative, you got to think a little bit about this one. If you round down to the next lowest integer from negative 1.5, what would your integer be? I think negative 2, right? Because negative numbers, you got to think about, here's negative 1, here's negative 2. If we're rounding down, we're going to get negative 2, because negative 2 is actually smaller than negative 1. So be careful on those. kind of did this one already, but we'll do it again. If I give the greatest integer less than or equal to 2.9, or I round down to the next integer, what would I get out of this? 2. Notice, we only get integers, which means your graph is going to have steps in it. And the nice thing is, it's very much a pattern. Once you get a couple down, you just continue the pattern. So let's see what a graph of this would look like. Questions about what this means? Greatest integer function? Let's look at a graph. And we're just going to start basic. Of f of x equals the greatest integer of x. Or we could write whichever way you want to do it. I'm going to pick some points here with an XY chart. When you're doing these, XY chart isn't a bad thing, but you've got to remember it's supposed to look like a step, because if you only pick nice integer numbers, you're going to look like you're graphing a straight line here. So let's pick a few points, and then we'll talk about what we should do here to make it look good. What happens if I pick something that's not a decimal? Like, what if I pick 0? If I plug 0 in that, what's the lowest integer greater than or equal to 0? Like, do I round that down to -1, or do I just get 0 back? Because it's the greatest integer less than or equal to x. If you plug in an integer, you're going to get out an integer. Just like for the therapist problem, if I plug in an exact hour, like 2 hours, I'm just going to multiply by $20 to get my total there. So if I plug in 0, I'm going to get 0. I'm going to skip some space here because we're going to go back and put the decimals in. But if I plug in 1, what am I going to get out of that? 1, right? If I plug in 2, I'm going to get 2. So I just want to caution you about picking nice numbers on this. Because once you get the pattern, you could do that. But if you just graph those, you're going to make a straight line, and that's not what a step function is supposed to look like. Yes? Yes? What if I pick like 0.2? What would I get out of that if I plug in 0.2? 0. What about 0.7? Would you agree, based on the definition of this function, every number between 0 and 1 leading up to 1 is going to round back down to 0? Do you agree with that? And so think about what we did with the open circle, closed circle on the last one. I'm going to make my graph a little bit bigger here. I'm going to make this a 1 so that I don't have to do so many. So I'll make each one be like a half. So because I know every number between 0 and 1, like I know at 0, 0 there's a point. I know at 1, 1 there's a point. I got to show that step. How long is the step? Well, everything from 0 all the way to 1, but not including 1, so how do I show that? I make an open circle, is going to round back down to 1. And then once I get to 1, I'm going to jump up here. And what could you tell me about every number between 1 and 2? What's that going to do? It's going to round back down to 1. And you could plug in a few if you want. Like 1.3 is going to go to 1. 1.765, also going to go back down to 1. Every number between 1 and 2, but not including 2, is going to round down to 1. The closed circles will be what you get when you plug in the integers, like 2, 2. And do you agree that every number between 2 and 3 will round back down to 2? Here's a nice thing. It's always a pattern. Once you get a couple steps, could you tell me where the next closed circle is going to be? 3, 3. You see how the closed circles are all in a lovely little line? You see how the open circles like that. And so that's why I say it's kind of like a pattern. Once you do a couple steps, just fill your graph in. I'm going to give you graph paper today. You have to make sure that you can show that the graph is going forever. Can't put arrows on this, so how do we do that? We fill our graph up. So I'm going to make this go to here, and then at 4, it would go up to 4, all the way to 5. Who has questions on where I'm getting these values from? Could I go the other way too? Could I go on the negative side? Why is it switched around? On the therapist problem, the closed circle was on this side and the open circle was over here. Because on the therapist, wasn't the therapist rounding up every time to charge us more? The definition of a greatest integer problem is it will always round down. So on these problems, Logan, unless it's a story problem, on our greatest integer problems, it will always be like this. The closed circle will be on the left and the open circle will be on the right because the definition is we're rounding down, not up. I couldn't think of a good problem that rounds down because it seems like everything in real life always rounds up because they always want to charge us more. You can think about the negative side if you want, or you can kind of just think about where the next point would be if I lined it up. But if I plugged in -1, I'm going to get -1, and everything between -1 and 0 is going to go like this. And again, look at my little lines here. Like you don't even have to really think about it once you get a few of them, because it's just going to match up here. So I skipped some points here, or made each one a hash, so I didn't have to make so many of these. And it'll be like this. You can always check, as long as you start in the right spot, it will match up like this. What if I asked you the domain and range of this problem? The domain is the x values. What are you allowed to pick for x? Or more importantly, what are you not allowed to pick for x? What could you never plug in here for x? What do you think? Can I plug in decimals for x? I shouldn't have erased my xy chart. I had 0, and then like 0.2, and 0.7, and 1, and 1.3. Can I pick negative numbers for x? Is there anything I'm not allowed to plug in for x? So even though this is kind of a weird graph, I think my domain is all real numbers. Do you agree with that or disagree with that? Although this kind of jumps around, if I follow each one of these steps, do you agree that every x value on my x-axis is actually getting chosen? Every number between 3 and 4 rounds back to 3. Agree with that? So all real numbers. What about the range? Is the range all real numbers? What am I never going to get on for a y value? Yeah, I'm not going to get a decimal. I'm not going to get a fraction. I could get a negative out of it, though, right? Because I do have these negative values down here. I just didn't make any. And when I plugged in -1, I got -1. So we need to say everything but decimals and fractions. What's the name of this function again? The greatest. Yes, but what's this? The greatest integer function. Integers. Integers are negative numbers, 0, positive numbers, but no decimals, no fractions. So the range is only integers. And so the way we can write that, can't really write this one in interval notation, but we could say y has to be an integer. So y is an integer. Because it's never going to give you those in-between values. Between 0 and 1, you're never going to get that y value. It's a step function because it skips some y values. What do you think about that? Should have done that in Algebra 2. That would have been exciting Algebra 2 stuff, right? Let's do another one. Tuesday, and it's a Friday. Later in this chapter, we're going to talk about transformations, which we talked about a lot last year in Algebra 2. And maybe you remember transformations, and you know what happens to this graph when you add a 3 out there. But if not, we're just going to pick some points here. Every time it's going to be those steps. So all you got to do is get a couple of those steps started, and then you can just repeat the pattern. So let's make a few points on the graph, not very many. Maybe like 4 each way. Oh, I went 5 there. What happens on this one if I plug in 0? Yeah, I'm going to get 0 plus 3, so I'm going to get 3. That is a solid point on my graph. Every time, that's going to be a filled in circle. When you plug in an integer, you get out an integer. And let's just go to the next integer. If I plug in 1, what am I going to get? 4. If you're not sure about the which way the step's going to go, plug in 1 decimal just to be sure. Like, let's plug in 0.5. Order of operations, we're going to do this first before we add 3. If I plug in 0.5 into this, what am I going to get out of it? 0, and then 0 plus 3. So based on that, do you agree that every fraction or decimal between 0 and 1 will round back to 0, and I add 3 to it, and I'll end up with 3 there? So that's your step. Notice it's still just 1 step wide. So watch what happens up here. Let me show you a little shortcut that I do, maybe. 0, 1, 2, 3. Graph your next solid point. 1, 1, 2, 3, 4. Wherever your next closed circle is, will be where the step below that ends. Does that make sense? Because once you step up, that means the step underneath there ends. And that makes sense. Everything between 0 and 1 is going to round back to 3 on this one, because of that plus 3. And then if you want to get the next solid point, what would happen if you plug 2 in there? 2 plus 3 is 5. 1, 2, 3, 4, 5. And guess what? Where that next solid point is where the step below that would end. Everything between, that's why I should use the graphing one, because this does not match up there. Everything between 1 and 2 should round back to 4. And then at 2, it would go up 5. Again, notice, although it's moved around, the solid dots are still in a line, the open dots are still in a line, and you just fill in the pattern. So you got to fill your graph in. If you only graph these 3 steps on your paper, I'm not going to give you full credit, because you need to show me that it's an entire graph that keeps going. So I'm kind of out of the top. How did I get this step?
Yeah. If I get this one.
You get the 1 to 4 part, right?
Yeah.
And so then if I plug 2 in, do you agree that you get 5 out of that? So if you get another solid point up here, that's where your other step ends. Like, the steps are always going to be the same length. And whenever you get another solid point, that tells me that the other point underneath it has to, like, that's where that step underneath there would have to end, because it's still a function. Or you could just pick some points. I was just trying to show you without having to pick points every time what to do. Whatever fills your graph up. So the less lines you make on your graph, the less ones you have to do. So I'm going to just keep going this way, and I know that this would be an open circle because it's underneath there, and I'm going to go back 1 length, because they're all the same length. It's not tricky here. And then I'm going to go down, and I'm going to make an open circle underneath that closed circle. And I'm not even thinking about the numbers at this point. I'm just following the pattern. Does everyone see what I'm talking about, following the pattern? Because I know that it just repeats itself over and over again. Sometimes when I was doing this on Friday, if you wanted to check yourself, like, you could plug in -3 and make sure that you really get 0 there to make sure that it lined up right. And it does. -3 plus 3 is 0. And I'm kind of out of points on my graph, so I would stop at that point. What about the domain on this one? All real numbers. Is the domain going to be all real numbers every time on a step function? Yeah, because you can plug in everything. It's always going to be, like, it's not continuous, but it's always going to be every x value is used, even though it jumps. Will the range ever be all real numbers on a step function? Never. And lots of times, like this one, what's our range going to be? Yeah, just like our last one, it's every integer. It skips every decimal, every fraction. So we're going to say y such that y is an integer.
Will the domain range always be there?
Well, I think we should do another one before we make that assumption. What if the steps were further apart? Do you think that could ever happen? You think maybe the steps could ever be like every other one? Like it would go from like 0 and then only at 2 and then only at 4? Yeah, I think if you multiply the x by a number, that can change that you wouldn't ever get an odd integer out of it. And I think maybe I have one more of these. Let's see. I do. Only it's a 3 instead of a 2. If there's nothing multiplied by x, Logan, you're right. Your domain and range will always be the same. But I think this is an example of one that could be a little different. So do like this last one. I want you to start this one. Pick a couple points. See if you can get a few steps. Notice I didn't make a huge graph here. I do have graph paper for you for your homework today, so that you don't have to make your own graphs. Well, I think you should use my graph paper.
I don't know. I hate algebra. I like the problems and stuff.
Oh, well, I have great graph paper. Look, you're going to be so happy. It's graphs with then white space.
That's acceptable.
That's acceptable. I'm glad I meet your approval. So what happens if I plug 0 in this one? You're going to get 0 because the greatest integer, again, I'm trying to write it both ways, but this is the same thing. What happens if I plug 1 in this one? Plug a number in between and see if you can get something besides jumping from 0 to 3. See if you could get a 1 or a 2 out of that. So what if you plugged in like 0.5? Do you agree that's still going to go to 0 times 3, which is still going to be 0? No matter what I plug in between 0 and 1, that's going to go to 0, and 0 times 3 is still going to be... What about that? What if you plug in 2? If you plug 2 in here, do you agree we're going to get 6 out of that? Is it going to jump from 3 to 6, or could I get something in between there? Like, what if I plugged in 1.8? Yes. Yes. Okay, thanks. Sarah, you're supposed to go to the office, but just hold tight for 1 minute, okay? If I plug in 1.8, am I still going to get 1 out of this? And then 1 times 3, am I still going to get 3? So this is an example one where the range is going to be different. So let's just graph this real quick. If I plug in 0, 0, let's just graph the solid points. So 0, 0, 1, 3, so 1, 1, 2, 3. Oh, I didn't even make enough points on my graph. Skip to the decimal. 2, 6. 2, 1, 2, 3, 4, 5. I'm just going to imagine where that next point is. Don't connect those and make a straight line because you know it's going to be a step function. Where's your step going to end? Wherever the next point starts. And so we already said we know everything between 0 and 1 is going to map back to 0. And look where that next step starts. It starts where x equals 1. So that's where you know to stop and make your open circle. But instead of going every integer, this one goes all the way up to 3. And everything between x equals 1 and x equals 2 is going to map back to y equals 3. How do I know where to stop that one? It's where this one starts. And again, that's why graph paper is so nice, because you can line that up a lot better. But those steps are spread out more. That's what multiplying by a number in front does to your graph. It stretches it out. I think I could fit one more down here. Where would I put it down here? Where would my next point be? Yeah, down here, this is going to be an open circle. It would map back to this. And I don't even have enough points on my graph there, but then it would be at -6, and that's really spread out. Is my domain still all real numbers? It is. How would we write our range on this one, you think? What would you say about my y values on this one? What are they going to be? Yeah, they're definitely every third one. Could we even say they're multiples of 3? So I think I'm going to say y such that y is a multiple of 3. Now I had more notes for this because we didn't even get to the piecewise functions. So this is going to change what your homework is tonight. We'll have to finish this tomorrow. So here we go. Right now, you can only do 20, 21, 23, and 42. So you only have 4 problems. But I don't like some of these problems, so I kind of made my new problems. So 21 and 23, I want you to cross out, like on 21, just cross out the -8 because it's just kind of a big pain to graph that big of numbers. So on 21 on your worksheet, it's just the integer of 3x. And 23, I just made my whole new problem here. 23, just kind of cross out what's there, and I want you to write that problem. And I have graph paper for you, if you want. Here, you can go. Only do the ones you've underlined, because if you look at those other ones, we did not do ones like that today. So unless you want to teach yourself how to do those. We will do the rest of this tomorrow, and actually you can fit this whole assignment on this one graph paper. So we'll just kind of add on to this tomorrow. There are examples of this in that handout I gave you at the beginning if you want more examples tonight. So make sure you change these two if you haven't already. And you only have to do 20, 21, 23, and 42.